So here's our first example. We have a pendulum. Somebody pulls it up to this point right here and they let it go. And so it swings down and it'll actually swing back and forth, but we are interested in what happens at the very lowest point, which is right there. Okay? So to solve this problem, we're going to start off by making a diagram, which I already have here. And on the diagram, we have to include a reference point for potential energy. Because potential energy is relative, we've got to say where we're measuring it from. So I'm going to call this y equals 0 right here. So for these problems, I'm going to have an initial height, I'm going to have a final height, I'm going to have an initial velocity and a final velocity, and then we might have a mass, and we might have work done, which is the energy transferred to or out of the system. Okay? It's raised to an initial height of 0.45, so this is 0.45 meters, and at the end of the problem, it's at the ground here, so h final equals 0. It's released from rest, so the initial velocity is 0 because it says it's released from rest. And we are trying to find the final velocity. Nowhere in this problem is the mass given, so we do not have the mass. But because energy is conserved, no energy is added to or removed from the system. So we're ignoring the effects of air resistance as it swings down. There's no other sources where energy is lost, so this is going to be 0. Okay? So in physics, when we use a principle, we state the principle first. So to solve this problem, I'm going to start by saying that I'm going to apply the work energy theorem, which is that the final energy of our system equals the initial energy of our system plus any work done. Okay? Now this is a principle. We're going to use it to build ourselves an equation. The equation we get when we do this is going to be the kinetic energy, 1/2 mv final squared. So the kinetic energy at the end plus the potential energy at the end, mgh final, must equal whatever energy we started with, so that's 1/2 mv initial squared plus mgh initial plus any energy we add or take away from the system. Okay? Now, it's easiest to clobber things that are 0, so since the work is 0, that term is going to disappear. And since the final height is 0, this term here is going to disappear. And since the initial velocity is 0, this term is going to disappear. And so our plan is going to be to solve what is left for v final. And we're going to solve it algebraically. We're going to find an expression for the v final right here. Okay? So if I just rewrite what I have for clarity, I'm going to have 1/2 mv final squared on the left side. And on the right side, I'm going to have mgh initial. All right? And I'm trying to solve this for v final. Since all the terms on the left and the right have masses in them, the mass cancels. And so we don't actually need the mass. I'm trying to solve for v final. I'm going to clear the fraction by multiplying everything by 2. If I multiply this by 2, I get v final squared equals 2gh initial. And so an expression for the final velocity will be 2gh initial. Since I don't care about the direction, just how fast it's moving, I'm not going to worry about the plus or minus. So there we go. We have an algebraic expression for the final velocity. To evaluate that expression, I'm going to put in 2 times g, which is 9.81 meters per second squared, times the initial height, which is 0.45 meters. Take the square root of the whole mess. And when I do that, I get a final velocity of approximately 3.0 meters per second squared. So we use the principle of energy to build ourselves an equation which we solve for the final velocity of the pendulum at the bottom of the swing, and we got 3.0 meters per second squared. Okay? That's example 1.